Today, we charge the batteries of our mobile phones by directly connecting them to the socket. But here's the problem. If you were to directly take a couple of wires from the batteries and connect them directly to the socket and say close the switch, then your phone will probably blow up because the voltage that you get from here is very high. You may have already learned it's about 200 volts. But even if you could solve the problem of the voltage, maybe we could somehow lower the voltage, even then your battery will not get charged. There's a very good chance your battery will just get spoiled. And the reason for that is because the current that we get from the socket, from the wall, is an alternating current, which means the charges are going to keep changing their direction of flow. So once they will flow maybe clockwise, and then maybe they'll flow anti-clockwise. And as a result, when the current is flowing in one direction, your battery might get charged, but when it flows in the opposite direction, it'll get discharged. It'll get charged and then discharged. And so your battery will not get recharged at all. It might even get spoiled. So in order to successfully charge the battery, we need to do two things. One is we need to lower the voltage. That's something we'll not focus on in this video. But the second thing is we need to convert this alternating flow into a direct flow, a one-directional flow. And that's what we will see in this video, how to do that. All right, let's open the switch. And our first step is going to be to lower the voltage. And that's done by using a device called transformer. Now you may have already learned about this or may not. It doesn't matter because we don't really care about how this works. All this does is it lowers the voltage. That's all that matters. All right, we don't have to worry too much about what it is. So maybe the voltage over here is 200 volt alternating. The voltage that we might get over here would be 5 volt alternating. So that problem is solved. Don't worry too much about that. Now comes the big problem. The current that we're gonna get, if we close the switch, let me just do that. Let's just close the switch and see how our battery will get spoiled. And let's assume these blue dots represent positive charges inside the wire. Now, of course, in reality, it's the electrons, the negative electrons that are doing the motion. But since the direction of the current is the same as that of positive charges, let's just assume some kind of positive charges are moving in the wire. Then it would look something like this. This is what they will do. They'll once flow in the clockwise direction and then the anti-clockwise direction. Clockwise, anti-clockwise. Your battery is getting charged, discharged, charged, and discharged. And that's what we need to solve now. So let's open the switch. That's what we need to solve. So how do we do that? Well, one solution would be to hire someone, ask them to sit right next to the switch, and then ask that person to close the switch only when the current flows in the clockwise direction. Maybe that's what we want. Maybe that's when the battery gets recharged, let's say. And open the switch when the current tries to flow in the anti-clockwise direction. So it will look somewhat like this. So you close the switch when the current is flowing clockwise, and now it's about to flow anti-clockwise, open. Wait, close. Clockwise, open. Wait, close. Open. Easy, right? The battery will get charged, no problem. But you can see that this is not a very practical method. I mean, in fact, the current is alternating 50 times per second, and no one is going to be able to do that, right? If only we had a way to automate this. If only we had some kind of an automatic switch which only allows the current to flow this way, but not in the opposite direction, that would be awesome. But we do have a device, a PN junction diode. This is exactly what we want. It is something that only allows the flow of charges in one direction, but blocks the flow in the opposite direction. And we may not be very familiar with this circuit symbol. Sometimes people might tend to get confused that which side is P and which side is N. Well, remember, this is the P side and this is the N side. But guess what? The circuit symbol is so great, you don't really have to think about which is P and which is N. You see, an electronic engineer doesn't even care which is P and which is N. Here's the way that person would think about it. You see, the arrow mark over here is telling us that this diode in this orientation allows the flow of charges upwards. All right, and it doesn't allow the flow of charges downwards. That's it. We don't even have to worry which is P and N. So if you want this diode to conduct, we have to put a positive here and a negative here, forcing the current this way. If you put a positive here and negative here, well, the current won't flow. That's all. Think of it this way. Don't worry about the P and N when you look at a circuit symbol like this. All right, imagine we want the current to flow through our battery downwards. Can you think how should we attach this diode over here? There are two options. One, we should attach it this way, or we should attach it this way. Can you think about how to attach that? Pause the video for a while and think about it. All right, let's do this. Since we know that the current has to be downwards, only downwards, we only want the flow in the clockwise direction. That's what we want. So over here, we want the current only to flow towards the left. So if we orient our diode this way, oh no, that won't work because this diode will only allow the flow in the opposite direction. Oh, we don't want that. We want to keep our diode this way. Now, it'll only allow the charges to flow in this direction, towards the left, but it won't allow the charges to flow towards the right. And there we have it. Now if we close the switch, let's just go ahead and do that. So let's close the switch. Then when the current is trying to flow in the clockwise direction, our diode is going to conduct, and I'm going to give it a green signal. It's going to conduct. But now when the current tries to flow in the opposite direction, nope, it won't allow. The diode will not allow the flow. And so again, when it tries to flow in the clockwise direction, the diode conducts. And again, in the opposite direction, the diode doesn't conduct. And so now we have successfully converted AC to DC. And this process in electronics is called rectification. And the circuit is called as a rectifier. So this diode itself is a rectifier. It's something that converts AC to DC. It's fun to watch, right? And by the way, the green and the red color are only for our indications. The diode is not really glowing, don't worry. Okay, let's open the switch for a while. And what we'll do now is we'll draw a graph. Here it is. Our graph is going to be the current along the vertical versus time along the horizontal. And you might see there are two graphs over here. And the current, by the way, is the current through the battery. In the first graph, it will be without the diode, without rectifiers. The battery will get spoiled, but anyways, the graph. In the second graph will be with the diode. All right. So let's see, again, let's get rid of the diode for a while. And let's see what the graph would look like if we had just closed the circuit over here. So let's just go ahead and close that switch. Close that switch. We've already seen the charges will flow in both ways. Once it flows clockwise and then it flows anti-clockwise. So what will the graph look like? Well, it's a graph of an alternating current. We'll call clockwise as positive, and let's call the anti-clockwise current as negative. Well, in that case, well, when the current is flowing in the clockwise direction, the current increases, becomes maximum, decreases, then goes to 0. Then the current starts flowing in the opposite direction, becomes maximum, goes to 0, again, clockwise, anti-clockwise, and so on. You may have already seen this before, but this is alternating current. Okay, now let's see what happens with the diode on. So imagine we just close the switch now. What do you think the graph will look like? I want you to pause the video and try to think about this graph yourself. All right, let's see. So during the clockwise, the diode conducts. It allows the flow of charges. So the current flows through. You get an exact copy of what you had before. But now during the anti-clockwise direction, when it's trying to flow anti-clockwise, our diode doesn't conduct. It doesn't conduct, so the current is 0. Can you see that? The current is 0. Now again, during the clockwise direction, it'll conduct. And so you get that exact copy of what you had before. But during the anti-clockwise, it doesn't conduct. It doesn't conduct anti-clockwise at all. So you get 0 current. And so by looking at the waveform, you can clearly see that in the second case, the current is only flowing in the positive direction, only clockwise flow. And so we will call this as the non-rectified current. And this is the rectified current. This is the rectified output current. Now notice that the current that is flowing here when the diode is placed in this waveform, notice that the circuit is only switched on during one half of the cycle, right? It's switched off for the other half. The half that we don't want, we just turn off the circuit. Again, we turn on and we turn off. This circuit is, this rectifier is called as a half wave rectifier for obvious reasons. It only works during the positive half, the half that we need, and just switches off when we don't need it. All right. And so the problem with this is that your circuit is off for half the time, which means if you're charging your phone with this half-wave rectifier and say your phone takes about 2 hours to charge, it means it was only, the phone was actually only charging for 1 hour. For the remaining 1 hour, it was just switched off. So a lot of time gets wasted. So of course we need to improve upon our design. But anyways, you get the idea of how a rectifier even works now. And one last thing is, whenever I should look at the circuits like this, I used to always wonder, like, how come there are two wires coming out of the phone? There's only one wire coming out, right? Well, this is actually a schematic drawing. Okay, a more realistic circuit would look somewhat like this. Notice the circuit is exactly the same as before, but it is made more efficient so that you don't waste a lot of space. Notice that the wires are actually, there are two wires actually bundled together and they come out of the phone together. This is packaged together. And where do you think are these transformers and the diodes? Well, they are found inside the adapter that we use. That's right, it's all packaged. Of course, there are more stuff today because we have better rectifiers, so there'll be more stuff, but all of those things are packaged in that tiny adapter. And again, this is bundled together so that end users like you and me, we don't have to worry about the science behind it at all. We can just plug in and charge our phones. Amazing, isn't it?